Welcome everyone for the afternoon session, and Gregory has kindly agreed to chair this session.
Okay, so good afternoon to everybody. So this afternoon we have two talks. First one by Vincenzo Alba, who will talk about a new QSSEP, toy model for entanglement spreading in diffusive systems. So please, Vincenzo.
So thank you very much. So thank you for coming. And of course, before starting, it's my duty and pleasure to thank the organizers for putting together this event and for giving me the possibility to speak here. So it's my first time in India, and I mean, this place is so great that I feel like I could stay forever. So okay, today, as anticipated, I'm gonna introduce you to this model, which I call a new QSSEP, and it's a toy model for entanglement spreading in diffusive systems. Okay, so I think actually that before starting, I can say a few introductory words. So I think this fits nicely in the topic of the theme of the event, because I mean, so far we've been discussing a lot that behind the GHD and also behind the MFT, there is the idea that you can take a unit cell, right? Sorry, a mesoscopic cell, and then you can imagine that the system is a collection of kind of independent mesoscopic cells, and then you know, if the cell is large but not too large, then you can cook up some effective theory. But this idea that the cells are independent, you know, it might fail. And in particular, there are some quantities in which you have to take into account that these cells are actually not independent. Okay. So, for instance, as I'm going to show, so if you want to measure entanglement, you have to go beyond this assumption. So, what I'm going to present somehow is, if you want a way to go beyond this idea of independent cell, or if you want, is an interesting direction. That tries to go beyond these assumptions. Okay, so so let's start. So this is the outline. So the broad goal is to understand better the interplay between entanglement out of equilibrium, meaning unitary dynamics, and dissipation. So what happens if you have at the same time unitary processes, but also you are coupled to a bath. So okay. And your system is a many-body system, okay? So many degrees of freedom, okay? To motivate what I'm gonna discuss, so the main topic, which is the QSSEP, I will start with a kind of brief excursion in the realm of Lindblad dynamics, okay? For quadratic systems. And I will characterize how, under some assumptions, you can describe entanglement dynamics in these systems, and then this gives the motivation to try to go beyond and then consider this this QSSEP, which in my opinion, exhibits a much richer behavior. Okay, and then I will take this model and I will massage a bit, if you want, to make it simple enough, and then I will be able to provide some exact results for entanglement dynamics. Okay, at intermediate times. Okay. This is the main goal that I want to achieve. So I think the audience is quite diverse, so a minimal introduction is kind of needed. So for what follows, it's important to know that if you have a system and you have a subsystem and you want to characterize the genuine quantum correlation between your subsystem and the rest, this is a difficult task, okay? Local observables usually are insensitive to this. So if you look at local observables, you don't have access to entanglement. But you know, there are some quantities like this quantity here, which is the von Neumann entropy, or alternatively Rényi entropies, which do the job. Okay, what you need to know is that if you measure this quantity, which is built out of the reduced density matrix of A, and this is non-zero, then you are sure that the A is entangled with the rest. There is quantum correlation between A and the rest. So for the first part of the talk, I will be in a kind of more difficult situation because, you know, this quantity is a good measure of entanglement only if the system is globally pure. But if you introduce dissipation, the system is not globally in a pure state, it's mixed. In this case, this quantity is pale to capture entanglement because the environment introduces some spurious correlations that pollute this quantity, okay? I mean, there is a quantity that you can use, which is so-called logarithmic negativity, which was introduced in these papers. This is still computed from the density matrix. Okay, you have to do this weird transformation, which is called partial transpose, and then look at the eigenvalues of this row transposed. These are not positively definite, so the negative eigenvalues somehow it's proven by quantum info people that have to do with the entanglement. Okay. Now, these quantities, you would like to understand how these quantities behave when you take your system and you drive it out of equilibrium. This is a very difficult task, okay? Out of equilibrium, many degrees of freedom, you are in trouble, okay? In some cases, you know, there is a simple picture that you can use. So if your system is integrable, actually, you can describe entanglement dynamics in terms of the quasi-particles that you have, okay? So an integrable system is supposed to have well-defined quasi-particles that live forever. What is this picture? It's the simplest thing that you can imagine. When you drive your system out of equilibrium, you can imagine of creating bell pairs at each point in space. These pairs are formed by entangled quasi-particles, and as they travel, they spread their entanglement, okay? So if a quasi-particle, if an entangled pair is shared between your subsystem and the rest, then it entangles A and the rest, okay? And then entanglement is proportional. For instance, the von Neumann entropy is proportional to the number of entangled pairs that are shared as a function of time. Yes? Yeah.
Up to now, things could be classical and one could do the same definition, except the quasi-particles, okay? But yeah, it could just as well be classical, or is there something inherently quantum?
That's an extremely good point. So everything here, almost everything is classical. So these particles, you treat them as classical particles. The only point where you know that they are quantum is in the fact that they have this pair structure. So this particle, even if it's here, knows that there is a partner somewhere else in the system. This is the only point where you introduce this quantumness in the system, okay? And actually, these correlations that you see, they are quite long range. Usually you don't capture them with GHD or with other macroscopic, yes, yeah, these correlations usually you have to go beyond the GHD, you have to go beyond MFT to capture this correlation, okay?
For the pairs of quasi-particles, if you take like a classical harmonic chain with a quench in the mass, you still obtain like pairs of particles, I guess.
Yes, so but you have to, you know, yes, that's also a good point. So, yes, but when you deal with a quantum system, it's the interpretation that changes. In that case, they are just independent. So the fact that the two particles travel in opposite direction doesn't mean that they are entangled. Here you impose that they are entangled, okay? It's the interpretation that you give that is different, right?
I wonder if you can define some kind of sort of classical correlation between the particles and that will spread as well. Like you don't have entanglement entropy for sure, but still, I think you're gonna see some correlation.
You would have correlations, of course, yes, but it would be classical correlations, and they wouldn't contribute to, of course, there would be any von Neumann entropy. In that case, they would contribute to classical correlations, yes.
Sure, thank you.
Okay, so, I mean, then the problem of computing the dynamics of von Neumann entropy is just the problem of counting these pairs of particles, and then the counting you can do easily, and you get this function here. So this function here is a function of time. It goes up linearly and then it saturates. Yeah. Okay. But then you know you need to provide some ingredients, which are these velocities at which the quasi-particle travel and the amount of entanglement that they transport. Okay, they share. And somehow, after a lot of work, which is the result of this paper, so you realize that in integrable systems, so these V are the group velocities that you construct considering excitations above the statistical ensemble that describes the steady state at infinite time. And this S of K is just the thermodynamic entropy of the generalized Gibbs ensemble. So you see, even though you are describing something that is really quantum, it measures quantum correlation like the von Neumann entropy, the ingredients that you need are classical. Okay? You extract them from the statistical ensemble. Okay. Okay. Now, so how do you understand this formula? So a good rule in life is when you want to understand something, you consider the simplest setup that you can imagine. And here, the simplest setup you can imagine is a chain of hopping fermions on a ring, okay, which you can diagonalize by going to Fourier transform. You can compute the dispersion, and then the group velocities, okay? Then you can perform a quench. You can take an initial state like this, which is a null state, so 0, 1, 0, 1, 0, 1, okay? And then you notice a very crucial thing. So if you consider the Fourier transform operator, CK, then you see that if you construct the, if you consider the expectation value of the initial state of C dagger K and C dagger CK prime, you see that this matrix is non-diagonal, okay? So it has a diagonal part, and then it's non-zero only if, also if K and K prime differ by pi. And this is due to the simple fact that you have a two-side translational invariant. This means that you can define two species of fermions, eta 1, which is CK, and eta 2, which is CK minus pi. Now, if you compute the correlation matrix, you have this form. And if you interpret these two, eta 1 and eta 2, as new species of fermions, you see that eta 1 is correlated with eta 2 because you have an off-diagonal element. This is what justifies the fact that you have pairs. So this eta 1 and eta 2 are the two quasi-particles, and since you have an off-diagonal term here, the two are entangled. Okay? You see that this off-diagonal term actually evolves with time, but it gets a phase. And in fact, as you go towards the steady state, what happens is that you have this phase, and this off-diagonal term will essentially die out. But it leaves a trace behind, because it's responsible for the fact that you have the pair structure, and the correlation between the pair remains forever, okay? Even though this off-diagonal element dies out. Now, in this simple case, you get, you can apply the formula of the previous slide, and then the group velocity is sine k, and then you can compute the thermodynamic entropy of the GG, which depends just on the off-diagonal elements, okay? It depends just on the density of these modes here, eta 1 and eta 2. And in this particular case, you get log 2, okay? The expression is here, okay? This is the thermodynamic entropy of the GG, okay? Yeah, it's called also Yang. Now, let's go to the dissipative setting, okay? In the dissipative setting, now our spin chain, if you want, our model is coupled to, let's say, some path in some way, okay? So you can imagine of applying the Lindblad description. The Lindblad description gives you an evolution equation for the density matrix rho, which contains a unitary part and some non-unitary term, which describes effectively the interaction between the system and the path. Now you see the problem is complicated because on top of the unitary dynamics, you also have some non-unitary processes. Now the question that I want to ask is it possible to generalize the formulas that I presented in the previous slides to this setup? Now, I cannot go into the details because this is supposed to be kind of an introduction to the main bulk of the talk, but what I can say is that under some assumptions, namely that the Hamiltonian is quadratic and these Lindblad operators are linear in the fermionic or bosonic operators, then this problem, this question can be answered positively, okay? And what you get actually is this. So this is, we derived it for the first time in 2021, but then it led to a lot of developments. So let us consider the von Neumann entropy of a subregion L in some scaling limit in which you send the time to infinity, L to infinity, you keep T by L fixed, but at the same time you send the dissipation rate to 0 and you keep this product gamma L fixed, okay? The dynamics of the fundamental entropy is described by this formula here. Now, let's have time to digest this formula, okay? So there is many ingredients there. So you see, unlike the unitary case, now you have a volume law term, which is this. And this volume law term, you interpret this as the density of entropy of the full system. Because now, so if you were a unitary, this term would be zero. But since you are in contact with the butt acts on the system and then it produces some entropy, even if you don't do anything unitarily within the system, okay? This other term actually looks very similar, actually is the same structure as the one that you have in the unitary case. You see, you have a mean 2 vk TL, V are the same as before. But you see, this you would interpret it as the entanglement shared by the quasi-particles. But you see that unlike the unitary case, now you have two pieces with a minus sign. So this is the same as this, so it's the density of entropy of the full system. This is a renormalization due to the action of the environment of the entanglement entropy that you would have without the butt, okay? So how do you compute this? So essentially, you look at the correlation matrix in momentum space, and you see how the diagonal elements evolve under the action of dissipation. Typically, they will acquire some exponential damping, okay? And then from this evolved diagonal elements, you construct what would be the Yang-Yang entropy. Okay? So you have a recipe to make this formula predictive. At long times, what happens is that these two terms cancel. And then you recover somehow the fact that you recover what you expect, that entanglement is suppressed at long times. But it's not suppressed because quasi-particles decay. They are alive forever. It's suppressed because the entanglement content that they have changes, okay? Now, so this is for, this is for the fundamental entropy, but as I told you, the fundamental entropy is not a good measure of entanglement. And you see it because here you have this volume law term. So you can compute actually the fundamental entropy, so the negativity. And this, took us a long time to realize this, how to do this. Eventually, with my PhD student, Fabio Jacopo, we managed. And we got a formula for the negativity. I cannot report you because it's quite complicated, but then you can check it in several models like Kitaev chain, XX chain, or even bosonic system like harmonic chain. And then you see the prediction is this red curve, and then these different lines here are exact numerical data. And as you go to the scaling limit, which is long time, large subsystems, and so on, they approach this red curve. There is something, an interesting point that I want to stress here. So to build this formula for the negativity, essentially, again, you have to go beyond hydrodynamics. So at least for free fermions, what you discover is that, if you have some correlations that are encoded in the off-diagonal matrix elements of the two-point function, you can actually transport them ballistically, okay? So it's not just the number of particles or local observables that you can transport using GHD. You can, as the quasi-particle travels, they keep the correlations that is encoded in the off-diagonal elements that you have in the two-point function, okay? This, I believe, it holds, at least in this form, only for free fermions, but, it's an interesting thing to notice, okay? Now you see that quite generically, you get that entanglement does what you expect. So it goes up, and then it goes down. So eventually, in the steady state, you don't have any entanglement. So you would like to go beyond and consider systems with a much more rich structure, okay? So to do that, I got inspired by this paper by Denis Bernard and Tony Jean in 2019, where they proposed this quite nice model Okay, so this is similar to the tight binding Hamiltonian. So you see, except for the fact that you have an infinitesimal Hamiltonian, and then you see you have hoppings, but the amplitude of the hoppings are stochastic variables in space and time. And they are like uncorrelated, okay? Both in space and time. Now, the first thing that you can imagine, sorry, this model actually arises in different contexts. So in the original paper, it was derived as an effective model describing the dynamics in a tight binding chain where each site is coupled with the path and essentially the interaction has the effect of dephasing, okay? If the interaction is stochastic, the dynamics of the system is described by this Hamiltonian in the strong dephasing limit, okay? Now you have an Hamiltonian which is noisy. What you can imagine of doing is taking the state and consider is the average over the noise. If you do that, you can derive the evolution equation for rho, and then you see that essentially what this amounts to is essentially random incoherent hopping. Okay, so you see the effective Lindbladians that appear in the Lindblad equation are essentially hopping terms. So this is essentially in the same classic or universality class of SEP, okay? At the level of the average state. But what you can do, actually, you can consider nonlinear quantities, nonlinear functions of rho, and then, of course, when you take the noise average, the story becomes much more complicated and you get much more rich behavior. So, for instance, in this paper, what these people did was to consider the entanglement entropy, okay, of the state. Now, the entanglement entropy is a nonlinear function of the state, and I mean, these people managed to compute the full counting statistic of the fundamental entropy in the steady state, okay? But as far as I know, in the literature, there is no result for the dynamics of any entanglement-related quantities at intermediate time. If you do the numerics, you see that it's diffusive. You can do it easily because actually for each noise realization, this model is quadratic. So Wick's theorem applies, so you can compute a lot of stuff. After you take the noise average, of course, the story becomes more complicated. So to address the intermediate time dynamics, I tortured a bit this model. So I tried to simplify it a bit. So what I did was to put back some structure in the noise. Okay. Now the noise in the QSEP, noise on each site is independent. Here, what I do, essentially, I introduce some periodicity in the noise. So I consider, I define the noise on a unit cell of size nu, and then the unit cell is repeated over the chain. For nu equal 1, essentially, I have just one noise, okay? One noisy variable on all the sites. Of course, it's still random in time. Okay. Now, the good thing about this is that you can go to momentum space, so you can define the two-point function, and then you do Fourier transform. And after you Fourier transform, essentially you get g k of q, where k, q are momenta, but also you have alpha and beta, which are the cell index. Okay. So for these are essentially for fixed k, q is a nu by nu matrix, and you can derive the evolution equation for the two-point function. Okay. In momentum space, and you get this kind of complicated equation, okay? And it's a linear equation, but still, it's a system of linear equations. It's not so easy to solve it explicitly, okay? Now, what you can do first is to go to the steady state. So you look at these equations and you ask yourself which of these correlators attain a non-zero value in the steady state. And then you can open Mathematica, you can do some computation, and then you figure out that there are some simple rules that you discover. So for instance, the one-point function in the steady state is typically decaying exponentially, you see it from this equation, except when the momenta are equal, okay? And also when the cell indices are equal. This is the only configuration that is non-zero in the steady state. And you can also you know, one reason why I decided to work on this is because you can produce nice pictures. So, so you can represent pictorially this object here in this way. So with this circle. So this is meant to be. So the black dot is momentum. So you see, you start from K and you end up in K. And here I do not report the cell indices. Okay, for now. You can also look at the second moment of the correlation after you noise average. And then you see that there are only few combinations of momenta which are non-zero in the steady state. So you see clearly that there is a rule. So the rule is that at each dot, you have to have a conservation of momentum, okay? Except for this last diagram where you see at each dot and also at each dot, there are two inflowing momentum lines, okay? This is open, sorry, this is periodic boundary conditions. It's, yeah, it's a periodic, not homogeneous, it's periodic boundary conditions. You might call homogeneous, but okay, I think periodic boundary conditions is more precise. And here, sorry, this is for nu equal 2, which means that you have a unit cell of two sides, okay? Now, this tells you which momenta, which quasi-momenta configuration gives non-zero value in the steady state, but you have also to look at the cell indices, okay? So for a given of these diagrams, you have only some configurations of alpha, of rho and sigma that correspond to non-zero correlators. And again, you discover some nice rules. So for instance, given this object here, now with the red line, I denote the cell indices. I have only two possibilities, 0 and 1, because nu is equal to 2. And then you see that this object here has to be equal to this. So in formulas, this means G00KK, GQQ00 is equal to, well, KQ0011, okay? And you have a whole set of rules, you know, you have also this kind of diagrams, okay? And this one appears here, and it has this -1, and you will soon discover what it is. Now, how do you derive these identities? Essentially, let's do it for the second moment of G. You can write the Liouvillean that determines the dynamics. In this case, it's a 6x6 matrix. And to get these rules, you have just to look at the eigenvectors that correspond to 0 eigenvalues. You have to look at the kernel of this matrix. And then if you look at the wave functions component for the corresponding eigenstates, you find out the rules, okay? You find out the rules that I presented in the previous slide, okay? For the second moment is easy, 6x6. For the third moment is 90x90, I think. For the fourth moment is 900x900. But okay, you can do it. Another thing that you discover is that there are conserved quantities.
I mean, what are these notation? -5, 1, -1?
Ah, yeah, sorry. Yes, sorry. This is just the identity matrix, and I think this is the matrix with all ones, 6x6. Yeah, it didn't fit into the slide, so I had to introduce some. But it's simple. Yeah, it doesn't depend on momenta. Okay. You have conserved quantities. Some of them are easy. So you know, this is the trace of G square essentially. This is the product of the trace of G, and this is the determinant. Is the determinant of G. Okay. Now, so I mean, you can get. I mean, you can actually use the information about conserved quantities to determine all the correlators that are non-zero in the steady state. Okay. So because you always have enough number of conservation that allow you to determine all the non-zero steady state correlators. Okay. For instance, here for the second moment, these are the relations between by inverting this system, you can determine all the steady state non-zero correlators in terms of these conserved quantities. Okay. Now, what is behind this? And you know, you have also some more funny correlators, but what is behind this? So behind this is the fact that actually there is some invariance under some random matrix ensemble. This is similar to QSEP. Okay, in QSEP you have essentially invariance under SUN matrices. Here is a bit different. So you can argue actually that given a string of correlators, if you take the noise average, the only thing that is non-zero are the combinations that are invariant under R average with momentum-dependent matrices. Okay, you see, so here you have G, K, KL, QL. You are allowed to multiply left and right with two different matrices which are momentum-dependent. And these V are random SU2 matrices for nu equal 2. And in general, one can imagine that you have SU nu if you have a unit cell of size nu. Actually, for SU2, of course, it's simple because then you can use a simple, Weingarten calculus, because essentially the only thing that you have with SU2 is the only invariants that you have are the traces or the determinant, okay, which is given, which is encoded by this the antisymmetric tensor, okay. And then if you unwrap these expressions, you discover all the relationship that I found in the previous slide, okay. This actually allows you to compute any function of the correlator G in the steady state just by taking the initial one and performing the R average with these matrices. Okay, these M are the inverse Fourier transform of this block diagonal matrices. VK is a random SO2 matrix. Okay. Now, okay, this so far so good. I mean, you discover that there is a non-trivial steady state because, you know, after you take this disorder average, this correlator do not obey Vic. So somehow you go beyond free Ferdinands. You start with the free Ferdinand model, but then you perform a noise average and you discover some non-trivial correlations in the steady state. Now, I want to, you know, I want to do something a bit more difficult. So I want to show you that actually you can go beyond the steady state. You can actually compute the full-time dynamics of the von Neumann entropy, with the caveat that I can do only in a simple case. Okay? Now I go back from nu equal 1, sorry, from nu equal 2 to nu equal 1. So now instead of having a 2 by 2 random SU2, I have a phase, because for nu equal 1, you have a random phase. Okay? In this case, I can perform calculations, and then I show you how to get to the end. So the model is essentially the same as before. I consider an initial state, which is of this form in momentum space. I can take an initial state, which in momentum space has a correlation function that is essentially a delta k of q plus delta k of k and q plus pi. Okay, for instance, a two-side translational invariance is of this form. Two-side translational invariant initial state is of this form. Now I want to compute the dynamics of the von Neumann entropy, and for each noise realization, the system is quadratic. So I can write it in terms of the two-point function restricted to the subsystem of interest. Till this is an horrible calculation. Okay. The way you do it, this actually dates back to a paper of Maurizio Fagotti 2008. The same strategy applies here. A similar strategy applies here. So you first compute the moments, GA to the power n, noise average. And then if you know the analytic dependence on n, you can essentially get any analytic function of GA. Okay? Even the von Neumann entropy, which is given by this. So let's do it. This is what you have to go through. Okay? Mn, you have to write it as a 2n dimensional integral. Okay? Then you have these products. You have a string of g's. These are simple functions. Okay? And then you have to find your way out of this, this beast. Okay? What is the trick? So you can massage it a bit. You can write in this form. Okay? Now you remember that you want to go to the hydrodynamic limit. The dynamic limit means that you want to go to large L and long times. Now what happens? In the large L long times, you can argue that you can use some stationary phase approximation. Let's look at this term. What does it mean? It means that if I go to long time, the momenta, they want to become all equal. Okay? So this means that everywhere in this expression, I can replace the momenta with just, they become all equal, okay? Except where I have these phases where I have to be careful. Because if I put the phases equal, I get a trivial result, okay? Now, let's look at this term. What I have to know are these epsilons, which are the eigenvalues of the Liouvillean that gives the dynamics of Mn. And this, for nu equal 1, you can get it analytically for any value of n. And you get these combinations of cosines. Now here, you should notice that what you have is a difference of momenta. If you were unitary, you would have just a cos of k, j, let's say, okay? Here you have differences. And this means that when you take the larger limit, you can expand this momenta, these cosines, sorry. And then you have something that goes as k squared. And this immediately tells you that you have diffusion, right? So here is how diffusion arises in this model. Okay. Now you can compute, you can go to the end, and then what you get is this formula here. So this is the final result. So I can compute any function of the restricted correlator GA, and the result is given here. Now we have to understand the structure of this result. Again, we have two terms, max L minus 2 psi 0, f lambda plus f lambda minus, plus mean. This is similar to the usual quasi-practical picture. And then you have a capital F of this f, little f, which is the function of momenta that you have in the two-point function. What is the interpretation here? Essentially this. So you can imagine that after the quench, in your system, you still produce entangled pairs, but now the entangled pairs undergo two correlated Brownian motions, okay? So you see this psi is the distance traveled by the quasi-particles as a function of time, and is distributed with the usual diffusive kernel, okay? And then this max L minus 2 psi 0 counts the number of pairs that at that time are within A. And this is the contribution that you get to the quantity, to the generic quantity F. And this is just F computed over the 2x2 matrix G. Because this lambda plus and lambda minus are the eigenvalues of this 2x2 matrix. This other term here instead counts the number of pairs that are shared between A and the rest. In fact, you get the same function mean 2 psi L that you get in the unitary case. Okay? Now, depending on the function that you choose, you have either both terms or maybe one of those, only one survives. If you compute the fundamental entropy, so if you choose F appropriately, right? What you get is that this vanishes and you are left with this. And then you recover this function here. So this is the prediction for the dynamics of fundamental entropy in this system. And you see it has this mean function. You have a P of psi, which is the probability of the Brownian particle to travel at distance psi at time t. And then you have Sn. Sn here is the same entropy that you have in the unitary case. So what you learn here is that in this simple setup, so essentially the quasi-particle contain the same entanglement that you have in the unitary case without noise. The only difference is that now the trajectories are not linear, they are Brownian motions, okay? Now, you know, we suffered through this calculation, but then, as usual in life, you discover there is a shortcut, okay? And the shortcut is the following. So since nu is equal 1, the noise is homogeneous, I can take the Fourier transform from the very beginning, and then I see that I have, you know, I have a d epsilon tk, which is given by this. And then I can integrate, and then I get epsilon k, which is two times the real part of wt e to the ik, where wt is a complex Brownian motion. And then if I believe the quasi-particle picture, I can take the formula in the unitary case, and I replace epsilon prime, which is the velocity, which is this term, and then I take the noise average. Of course, you are assuming that the quasi-particle picture, so this is not ab initio proof as the one that I provided earlier, but you can do it, and then if you perform the noise average, you recover the same formula, this formula here. Okay. Now, you can actually check that everything works. So, for instance, here I check the moments of GA. So, I mean, these are some, these blue lines are some numerical data for 2 different system sizes, blue and black line. And this dashed dot line is the formula, okay? For this Snell quench, I mean, you have very little corrections. You can do another quench from a different initial state, and you see you have some finite size corrections. But then as you go to long times, you recover the result, okay? So finally, you can check the dynamics of the von Neumann entropy, okay? You get this diffusive dynamics, which you can describe quite well with the formula, okay? Again, for the quench from the Dimer state, you have some more corrections, but if you extrapolate the thermodynamic limit, you recover the formula. So, yeah, okay. This is an important point. So you can compare the dynamics that you get from this new QSEP model with that you get from the QSEP. And then you see that already at nu equal 5, essentially you get the same dynamics as in QSEP. Okay? So this model is actually not far at all from the typical dynamics of QSEP. So I don't have enough time to describe that you can compute also the moments of the fluctuations of the von Neumann entropy. You can do it. So we did it in this paper. But I think I just leave you with the conclusions, and I thank you again for the attention.
Thank you very much for this very nice and clear talk. We have time for questions now.
All right. What's the point of taking different nu? This I miss it.
Sorry, what's the point of?
Why you want to take different nus?
Because at intermediate times, at least for nu equal 1, I can hope that I describe because I can hope to describe the finite nu case analytically, and then I can approach the QSEP as a limit nu becoming large.
But because the calculation in QSEP would be too hard.
At intermediate times, yes. Actually, in the steady state, I think it's simpler to consider the QSEP because the random matrix ensemble, I think, is even, yeah, it's easier because it's just SUN and there is no momentum dependence. But at intermediate times, it's difficult to get the dynamics, even though you know it's diffusive. So here, for nu equal 1, of course, it's kind of simple, but still, you know, it's not far from what you get in QSEP. If you know, I mean, then you can consider nu equal 2. And this is what I'm doing now. So nu equal 2 actually is interesting because you see that you go beyond the free fermions. So if you want to, you see that if you try, you can derive analytically the hydrodynamic formulas for the first few moments of the correlation matrix. And actually the first 3, they behave like diffusively. The same formula that you get from the nu equal 1 case apply with a different diffusion constant. If you go to nu equal 4, you have to get some. You have to use some Bethe ansatz for the eigenvectors of the Liouvillean to get the result. Yeah. So you see, it's there is some nice structure.
So the kind of hand-wavy calculation that you presented, maybe you can do something similar for higher nus, like without the full derivation.
That's a very good point. I think it doesn't apply. No, we tried, but I think it doesn't apply.
And picture should also hold.
I mean, if I try to find the eigenvectors of the Liouvillean, I get some non-trivial equations. So which means somehow that, I mean, if I get non-trivial equations there, I start to believe that I can bypass this with this.
That means that you would have a kind of other process that describes this.
For instance, you have you still have diffusion. You have a diffusion for any nu. It's just that diffusion. For instance, you have. I think you have interactions between more than 2 particles.
Other questions? Yes, please, Dima.
Just in the very beginning of your talk, you said that you need like a 2 by 2 structure which is induced by this Snell state. What happens if I don't have a Snell state?
Yeah, that's a very good point. I didn't have time to discuss it. It's a very interesting point. So what happens is that if you have this 2x2 structure, this you have in this model for the Snell quench, or let's say you take Ising chain and you do an arbitrary magnetic field quench, you end up always with this 2x2 structure. Actually, this 2x2 structure is what ensures the fact that in this formula, the entanglement carried by the quasi-particles is the thermodynamic entropy of the GG. So if you don't have this structure, so you can imagine, for instance, of having a larger unit cell, then this matrix will be larger. Then the correspondence between the von Neumann entropy and the thermodynamic entropy that you put here breaks down. You can still use this formula, but then it's more complicated. And what you have to put here is a non-trivial function of this matrix. So it's kind of accidental that if you have a 2x2 structure in the dynamics of the von Neumann entropy, you have the thermodynamic entropy of the GG. Okay.
Thanks.
Okay, if there are no other questions, let's thank Vincenzo again.